Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 78 in our incredible new tutorial series where you're learning how to think like an engineer using the Arduino Uno R4 Wi-Fi. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Elite Explorer Kit. Now, hopefully most of you guys already have your gear, but if you don't, take a look down in the description. There is a link over to Amazon, and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot simpler if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. What I'm going to do is I'm going to show you my solution to the homework assignment that I gave you in lesson number 77. But I must first ask, how many of you were successful? If you were successful, leave a comment down below. I am legend. Double chest bump. And if you were not successful, leave a comment down below. I folded up like a cheap Walmart lawn chair. Okay, now I think what you guys found probably was it was very easy to do the assignment, which was to just add the third axis, add measuring the Z axis acceleration in addition to the X and the Y, but you might have found a little bit of an unexpected result, and that's what we're going to talk about today. We're going to do it. We're going to look at the unexpected result, and then we are going to kind of think through things a little bit. The other thing that I want to show you as we're moving forward in this class, it's very hard to be looking at the data as it's streaming by, acceleration X, acceleration Y, acceleration Z. It's hard to look at that in a tabular format. And so what we're going to look at today is looking at the data graphically using the serial plotter on the Arduino IDE. I'm not sure in this class if we've used the serial plotter or not, but it's a very useful feature, and we're going to talk a little bit about that today because it will be helpful as we move forward. Okay, so let's see. What I'm going to need you guys to do is come over to the most excellent www.toptechboy.com. Let me go ahead and get out of your way. And then once you get here, I need you to search using this happy little search tool here. Search on something like add an MPU6050 accelerometer to your Arduino project. You'll come here. A couple of things you'll see is this is that's kind of a sorry about that ad. This is a very simple setup to connect the GY87 module to your Arduino. It's just SDA to SDA, SCL to SCL. VCC goes to 5 volts and ground goes to ground. So that's pretty easy. And then we're going to start with the code that we left off with last week. So we're going to snag that code, and then we're going to come over here to the Arduino IDE, and we are going to paste it in. And now we're just going to go ahead and run it to make sure that the world is in proper operating condition and we can copy and paste without a problem. Okay, looks like it is downloading all right. Okay, and we're getting the acceleration in the X and the acceleration in the Y. And let's see here if we can make sure that we're getting some live signals there. So what I'm going to do is I'm going to start by letting you see what I'm doing. Okay, I'm going to kind of put it against this book, and so I can just move it in the X direction. And when I do that, what you can see is that first number is changing and the second number isn't. And then if I put it this way, I'm going to move it in the Y direction. And similarly, that second number is changing and the first number is remaining constant. So we're getting an acceleration in the X and we're getting an acceleration in the Y. Now, what do we want to do? We want to measure the Z. So we're going to come up here to the top and we're going to need to create another variable, which is going to be float AZ. That's not a big surprise, is it? And then we're going to come down here, and let's see what else we're going to need to do. We get the event. It's going to get all the accelerations, but now I've just got to pull off the Z. And so I'm going to say AZ is equal to A dot acceleration dot Z, and then again we're going to divide by the 9.81, and that way we will always be getting a number between 0 and 1, right? I want to think in terms of G's, and so the acceleration of gravity is 9.81 meters per second. So if I divide by 9.81, then 1G becomes 1G. Okay, so we can think in terms of G, which to me is more intuitive than to think in terms of meters per second, but that's just me. Okay, so that looks good. Now we print AX, we print AY, and in this case, we don't want to print LN just yet. So I'm going to do a serial.print, and then what am I going to print? I'm going to print another comma, and then our friend the semicolon, then serial.print, okay, and then AZ. Okay, and then that should be a serial print ln, because it'll take us then to the next line. Okay, so now let's go ahead and let's download this, and let's see what happens. I hope I didn't make a mistake in that 3 little edits that I did there. Okay, it's looking good. It is downloading. Okay, it is done, and boom, look at that. But what do we see? What is the unexpected result? I'm getting very close to, in the X direction, 0 G's. I'm getting very close in the Y direction of 0 G's, indicating it's not moving in X and it's not moving in Y. But what is the unexpected result that I'm getting in Z? It is measuring 1G. Okay, even though it's not moving, it is measuring 1G. And why is that? Were you able to think through this and kind of get in your head why that was happening? Okay, well, let me come over here and try to draw this up so that we sort of understand this a little bit better. So let me go back and let me draw my picture of the accelerometer again. Okay, so I'm going to come here and I'm just going to draw the picture of the kind of cartoon version. I don't like that for an accelerometer. An accelerometer should be blue, not green. Okay, so what I'm going to do is I'm going to come here, and let's say that's the top plate, and then down here is the substrate. Okay, and now what we'll do is we'll come in, and remember we have these springs that hold the plate up. Again, this is kind of a cartoon version of it. All right, now, while this is sitting on the table flat, what is it experiencing? The acceleration of gravity is pushing down on that plate. The acceleration of gravity is holding it down on the earth. So if you think of me sitting in this chair, gravity is pushing down on me with a force, and that force is keeping me in the chair. Okay, the force of gravity is keeping me in the chair. But now, is there any force on me to the left? No, there's not. Is there any force on me to the right? No, there's not. The force is what? The force is pushing down. And so if you think of this plate, the plate has the force of gravity that's pulling it down, and so it is going to have, even though it's not moving, even though it's stationary, that plate is being pulled down against those springs by how much? By exactly 1G. Now, if I took this and I stood it up that way, Z would read what? Z would read 0. Why? Because in that orientation, there's no force of gravity. There's no force on it to the left or the right. But what would happen? What would happen now, the y-axis would start seeing that force associated with gravity. Okay, so this is one of the things that you got to get your mind around on the accelerometer. There's always going to be one axis that is seeing the acceleration of gravity, that force of gravity. All right, there's always going to be one axis. Now, if we tilt it at a 45-degree angle, then there's going to be two that see a partial g, a partial of 1g. Okay, does that make sense? Let's come back over here and let's play with this, okay? All right, so now what you're doing is you're looking down here and you see z is reading almost 1g, 0.95. Okay, it's reading almost 1g, 0.95. Tell me what's going to happen if I just turn this, and you guys need to see. Okay, let's make sure here. Okay, you guys need to see what's happening. And I think this is the view we need where we can see both of them. Tell me what's going to happen if I turn this upside down. If I turn it upside down, what happens? I'm reading now minus 1g. Why? Because now the plate is being pulled away from the substrate by the acceleration of gravity. Now what's going to happen if I come up like this? Okay, so now what we're seeing is I've put the x-axis up, and now what axis is seeing the 1g? The x-axis is. The x-acceleration is. If I turn it like this, what is happening? Now it sees the minus 1g. All right, now for y, if I put y up, now it's seeing minus 1g. What is x and y, x and z? X and z are 0. And if I go like this, y is 1g, and then the x and the z are 0. Okay, so what we have to see is that you are measuring the force of acceleration. If you move it, that is acceleration, and that generates a force. If you're sitting still and feeling the acceleration of gravity, that is a force even if you are not moving. So think of it this way. If you're in your car driving down the highway, what do you have? You have 1g pushing you down in the seat, but you don't have any g's forward or backwards. Why? You're at a constant velocity, no acceleration. If you wham on the brakes, you still have the 1g from gravity pressing you down, but now you have a g force from deceleration that's pushing you forward. Does that make sense? Okay, I hope it does. Okay, what I'm going to do now is I'm going to show you kind of a cool thing here that if you just come, you're going to have to come back over to this view. And if you just click this little line up here, you will get a plotter. And what that plotter will do, it will plot the data that you are continuously printing if you have a comma between it. So what am I printing? Acceleration x, comma, acceleration y, comma, acceleration z. So I'm printing x, comma, y, comma, z, and then I'm printing that over and over. If we come up here and click on our serial plotter here, what we are going to get is we are going to get a plot of those three numbers. Okay, what do we see? We see value 3, which is z, is up here at 1, and then the x and the y are very close to 0. Now, let me again put this where you can see. I want you to see what we're doing here, and so this is the view we want. Now, watch this. As I begin to tilt, what starts happening? It looks like I'm losing my signal there. Okay, I think I need to reset this. Okay, there it goes. Okay, this USB cable gets a little goofed up. So as I tilt, look what's happening. As I tilt, the X is coming up as the Z goes down. All right, now what do I have? Now I have the X at 1 and the Z has gone almost to 0. What if I come up like this? Okay, the Y goes to -1 and the Z goes to 0. So you see, we can see this data a lot better, and it's a lot easier to watch. It's a lot easier to watch if we look at it on the plotter than trying to look at those numbers. Now, what I'm going to try to do is I'm going to try to change X without changing Y or Z. And what do you see? You see value 1 going up and down. Now let's see if we can do Y. Okay. Y is going up and down and the others are staying. Now to do Z, I would go like this, and you can see I'm getting a Z signal without getting the X and Y signal. So that's pretty cool, and those are going to be the signals we're going to be looking at moving forward. But what was it we didn't like? It was giving us labels of like value 1, value 2, value 3. What we would like is we would like to have a legend that actually showed us a color code so we really know what we're looking at as this begins to get more complicated. So I'm going to show you real quick how that you can do that. And what you do is if you want to put a label on AX, before you print the data AX, I'm going to say serial.print, and then I'm going to print the label, which is AX, and then very important, you have to put a colon. All right, and then the semicolon. All right, then very similarly for the other two, okay, for AY, I need to put the label AY with a colon, like that. And then the same thing for AZ, and here we're going to put the label AZ. All right, so now let's run that, and let's see if that puts the labels up at the top like what I want. At least it's compiling. That's good. All right. And here we go. And let's get that plotter back up. I apologize. It throws it to a different screen every time. Okay. And look at that. So what do we have? AX is blue. AX is blue down here. AY is orange, and AZ is up there. So that is exactly what we wanted to see. Now, one of the problems is, like, if we start moving this around, what you see is it starts auto-scaling, and that auto-scaling on the Y-axis is very confusing and annoying, and so I don't want it to auto-scale. I want it to just keep the same scale. And so what I'm going to do here is I'm going to come in and I am going to print. So I'm going to serial.print, and then I'm going to need to print the comma again. Okay, I'm going to need to print the comma. Okay. And then I'm going to need to not make that serial print line, because that will be only on the last one will be the print line. Okay, so I put the comma. Now I'm just going to print a 1. All right, so I'm going to serial.print, and what do I want the label to be? Well, I'm just going to put UL for upper limit. So I'm just printing a constant 1 so it doesn't downscale. All right, so I'm going to do that, and then I need my colon in there. Now I'm going to do a serial.print. And then I am going to print here just the number 1, like that. All right. Now I'm going to do a serial.print. And now this, I'm going to print the label. I'm going to print the label lower limit, like that, with the colon. Okay. And then I'm going to come in and I'm going to serial.print LN, because this will be the last one. I'm going to print a -1. So that should sort of lock your scale between 1 and -1, so it doesn't keep rescaling, if I am thinking about this right. All right, so let's put that in. Now let's run this thing and let's see what we get. Okay, here we go. Looking good, looking good. Let's get the serial monitor up. All right, so we come over here, and what do we have? We have AX, AY, AZ. We have upper limit. I did not get lower limit, so I must have made a mistake in there somehow. Okay, after the 1, I do need a comma after that. Okay, serial.print. Okay, I forgot my comma. Like that. Okay, let's run it. Hopefully that was all that was. there it goes. Okay, we're going to come in and look at the serial plotter and see if we can get this over here. And boom, I have AX, I have AY, I have AZ. I've got the upper limit orange is 1 and the lower limit purple is -1. Now, if you watch as I'm turning this, you see I'm not auto scaling, right? I am not auto scaling, and so I can see really cleanly what the data is doing. Okay, so that is where we needed to be. What are we doing right now? We are measuring acceleration in X, acceleration in Y, and acceleration in Z. Very good. Okay, what is it that we don't exactly like? What we don't exactly like is I am sitting here still flat to the ground. I should be measuring what? 1G in the Z. But what am I measuring in the Z? If I can get this out of your way a little bit, I am measuring 0.95, so that's a 5% error. Now, if I look at AX, while it's not moving, it's measuring 0. And while AY is not moving, it's measuring almost 0. And so 0.02 instead of 0, that's a 2% error. 0.02 instead of 0, that's a 2% error. So it looks like I've got about a 5% error in the Z axis, and I've got a 2% error in the AX and the AY. Now, let's see if we turn it upside down, let's see what happens. So we were at 95, and now we are measuring about -1.1. Okay, it's measuring about -1.1. And so that's more like a 10% error in this other direction. Now let's just kind of check, like I'll check the X. The X is at 98 now, and that 98 would be a 2% error like we were seeing before. And then if I come the other way, it is a 1.03, so that would be a 3% error. Okay, but there's something very important I need you to see. So let's just look at Z again. So I'm at 0.95 when I'm up, so I'm 5% low, all right? And then if I come over here, I'm reading 1.1 if I just do it perfectly, so it's 10% high. So it's like in one direction, it's 5% low, and in the other direction, it's 10% high. So what we have to do is we have to calibrate this. And by calibrate, I mean if I'm in this orientation, it should be at 1. If I'm in the other orientation, it should be -1. If I'm like this, it should be 0. If I'm like this, it should be 0. And same thing for the other axes. They need to be +1, 0, or -1 at those orthogonal positions. And then if the orthogonal positions are right, then all the in-between positions would be right. But we have errors in our data. Now, let's come over here and talk about that, because this is what your homework is. Your homework assignment is to write some software that will come in and that will calibrate your sensor where you're at +1, -1, 0, okay, 0, like that. And all three axes read correctly in those orthogonal positions. All right, but you see, like if you think I'm reading, I'm sitting here and I am reading 0.95 when I want to be reading what? 1. Now you might think that you could just come in and you could say, well, I'm just going to add 0.05, and if I just added 0.05, then when I'm sitting like that, it would be reading right. But when I go the other direction, right, when I go the other direction, it was reading -1.1. If I just added the 0.5, then it's going to be reading -1.05. So it's still going to have a 5% error. So you can't just randomly add a number to make it work. And so what your job is for homework for next week is to calibrate these three sensors. Now I'm going to try to help you a little bit. Now let's see case 1. Case 1 would be that I'm reading between 1 and I'm reading -1. That's perfect. That's perfect, right? I wouldn't have to do anything. But let's say what the error was, instead of going from 1 to -1, let's say I was going from 0.5 to -0.5. Now, why am I doing these? Because I want to exaggerate the error so you see. What type of error is this? What type of error is this? This is a scale error. Now, if all errors were scale errors, I could just multiply by the error factor. Like here, if I just multiplied by 2, everything would work perfectly. So how do I take a scale error out? By multiplying. Okay, but there's a different type of error. All right, so what do we really want? We want to go from 1 to -1. But what instead of that, what if we were going from 1.5 to 0.5? Okay, now this is what? This is an offset error. This is an offset error. How would I fix an offset error? And let's say that this was going from, the right thing would be to call this, that this was going from 0, or this was going from -0.5, from -0.5 to 1.5. It's going from -0.5 to 1.5. -0.5 to 1.5, what is the scale? It's a 2, a scale of 2. That's right. So the scale is right. There's no scale error. What is the error? The error is an offset of 0.5. So how do you fix an offset error? You plus or you minus to take care of an offset error. So if you have a scale error, you would multiply. If you have an offset error, you would add or subtract. But what is our problem? Our problem is, in reality, usually we have something like this. Okay, let's say this one is off by that much, but this one is off by that much. So what do we have here? That between those dotted lines is more than 1. It's more than 2, I'm sorry. So we have what? We have a scale error. Okay, but besides a scale error, the upper and lower limit did not change by the same amount. So what do we also have? We also have an offset error. Okay, so if we're going to get this thing to read plus and -1 in all of the orthogonal positions for all three, we have to do what? We have to correct for a scale error and we have to correct for an offset error. Now, guys, I have given you a great, big, huge hint. I've given you a great, big, huge hint here in how to do this because I'm showing you how to think about it. Now, you got to go through and do a little bit of math. Now, the next thing I have to show you is don't assume that your desk is flat, and don't assume everything is perfectly aligned. I don't know if you can see this, but if this chip is not sitting, if this board is not sitting flat in your breadboard, if this module is not sitting flat in your breadboard, that is going to generate an error. And in fact, let me even see if I can show that. If you're looking at the Z, you see how you get a, you're not looking at that. Let me get you over here. Now look, just by me tilting, you see by me tilting the chip, you see we're getting different readings. We're getting different readings just by tilting the chip. So you can't just go in and say, okay, well, I'm going to say that this is reading 0.95 here because you don't know whether you're really absolutely flat with the ground. So what you've got to do is you've got to find that maximum value, and then you've got to find the maximum value. So you've got to find those endpoints, because you cannot assume that the chip is sitting in the board squarely flat, and you can't assume that the top of your desk is level. So you've got to go in and you've got to get those numbers that you're going to normalize to by doing a little bit of tweaking. Okay, I might as well just do the homework for you, right? I might as well just do the homework for you, but I want to see what you guys come up with for calibrating this. When the sensor is properly calibrated, your sensor should read between +1 and -1 on Z, and between +1 and -1 in X, and between +1 and -1 in Y. And with a properly calibrated sensor, that's what you'll be reading. And if your sensor is properly calibrated, then you're going to get much greater accuracy in the projects as we move forward. Sound good? I hope it does. Guys, this is the point in the lesson where I always give a big shout out to you all who are supporting me on Patreon. Without my Patreon support, I would not be able to continue to make quality, fresh content every single week. So I want to give you guys a thank you. You can also help the video by giving it a thumbs up and leaving a comment down below. If you haven't already, subscribe to the channel, and when you do, make sure you ring that bell so you'll get notification when future lessons drop. And most importantly, share this video with other people, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.